Hi everyone, I'm Abhishek Kumar and I have made a presentation on modern computer devices and Turing machine. So this is the table of contents in which we will learn about what is a modern computer, simulation of a Turing machine by a modern computer, handling infinite memory and Turing machine, handling an enormous Turing machine, the first decode execution cycle, and simulation of a modern computer by a Turing machine, simulation of an instruction cycle, handling input output, and running time simulation. So first of all, we will see about what is a modern computer device. So not a standard well accepted definition, but modern computer devices are laptop and desktop computers, servers, clusters, GPUs, supercomputers, computers in a network, quantum computers, FG, FPGAs, ASICs, embedded processor. Modern computer architecture are rather complex. How to make a mathematical model of such a machine? Let us take a laptop or desktop computer as a representative, and we will furnish so that such a modern computer is equivalent to a Turing machine. Okay, so these are all modern computer devices. So simulation of a Turing machine by a modern computer. So we do the simulation of the Turing machine in this way by a modern computer. If input is a Turing machine M and output W for Turing machine M, and output is a C program to simulate the work of M Turing machine on W. Seems like not big deal. And issue to worry about, a modern computer has limited memory, how to simulate the infinite tape of M. What if W is so large that it does not fit in the memory of computer? And what is sigma, what is gamma, and if M is too large? And the solution is use an unlimited source of external memory like pen drives. So handling infinite memory. So this is how we handle the infinite memories. Okay. So let the numbers of the pen drive we will use as 0, 1, 2, 3. Let C be the current pen drive in use. The pen drive storing the part of the tape to the left of the C, Cth drive are in the stack. Okay. And if the head wants to move to the left of the first cell of the current drive, then push the current drive to the right stack, pop and insert the drive at the top of the stack. If the head wants to move to the right of the last cell of the current drive, push the current drive to the left of the stack and pop and insert the drive at the top of the right stack. If the right stack is empty, a new pen drive is opened. So this is showing how we do insert. So now what is a Turing machine? So basically, a Turing machine is a mathematical model of computation describing an abstract machine that manipulates symbols on the strip of tape according to a table of rules. And despite the model's simplicity, it is capable of implementing any computer algorithm, any complex computer algorithm we can use. A Turing machine is a general example of central processing unit that controls all data manipulation done by a computer with the canonical machine using sequential memory to store data. More specifically, it is a machine automata, we can say, that is capable of enumerating some arbitrary subset of valid strings of an alphabet. These strings are part of recursively say. A Turing machine has a tape of infinite length on which it can perform read and write operations. So how do we handle an very enormous Turing machine M? So the input W for M may span across multiple pen drives. If gamma is very large, The entire memory of a pen drive may be insufficient to store a single symbol. For a 16 GB pen drive, it means gamma is greater than 2 to the power 13743895347 To solve this problem, encode the symbols in binary, okay? It breaks inside a tape of symbol that is allowed. There is now a reading mode to collect all the bits of an individual tape symbol and to interpret a bit of collection. This may increase the number of states of M significantly. The input W may span across multiple pen drives. M should reside in the internal memory of the computer. The internal memory is infinite and may fail to accommodate M. Solution: send M to the tape, that is a sequence of pen drives. Don't stimulate M on W. Simulate the universal Turing machine U. U simulates M on W upon the input of M on W on the tape. U is a fixed machine of moderate size. U fits in an amount of memory independent of M and W. So this is how do we do the fetch, decode, and execute the cycle. Each instruction consists of an opcode, that is operation, zero or more operands, we can say, and the destinations. A counter stores the address of the instruction to execute next. The opcode is first fetched, the opcode is decoded, and requisite operands are fetched from the memory. The operation is performed, the result is written back to the destination address. If the instruction is a jump instruction, the instruction address counter is written by the jump address. Otherwise, the counter is incremented to the address of the next instruction. Initially, the counter is loaded with the address of the first instruction. So, simulation of a modern computer by a Turing machine. M contains 6 steps. Okay, uh, where the M is our Turing machine. The first step stores the memory of the computer as W1, W10, W2 as 11, W3 as 100, W4 as 101, and W5 and so on. Where Wi is the content of the ith word encoded in binary. All the W's are encoded in our binary format. There is second step that stores the instruction address. The third step stores the operand address. The fourth step is used for a scratch work, and the fifth step stores the input of the user. Sixth step is used to write the output to the user, and the infinite step the controls stores the information of the instruction set of the computer. So now this is how we simulate a instruction cycle. We learned in this how to simulate an instruction cycle. To simulate an instruction cycle, we will first locate the word whose address is on the second step. Okay, read and remember the opcode in the finite control. You can also write that opcode any rough page, and copy the operand address, if any is there, from the rest of the instruction to the third tape. Okay, locate the operand address on the first step and copy the operand to the fourth step. Apply the operation on the operands on the fourth step, and the result is produced in the fourth step. Now locate the destination address on the first step and copy the result to the location, that is the reallocation of the rest of the step. If if it is a jump instruction, then replace the second step by the content of the third step. Otherwise, increment the second step by an appropriate amount. So this is how do we handle input and output. Input and output are not part of the computation. Okay, so there are a specific read write instruction instead of input and output. Input is like writing and output is like reading. The read instruction scans the input from a specified address on the fifth step or sequentially. The write instruction, it will print the output to a specified addresses on the sixth step or sequentially. Now peripheral devices handle these steps. The keyboard control can write the fifth step. The screen controller can read the sixth step to change the display graphics. M may have an accept a state T and reject a state R. Upon successful or unsuccessful termination, M goes to T or R and halts, means ends the program. Now, this is how do we do the running time of the simulation. Suppose that the computer takes n steps for some computation, okay? Now, we will assume that the words of the computer are fixed size, like 64 bits. Overflows during arithmetic operation are ignored. It can be calculated that the simulation by the Turing machine requires big O of n cube steps. If n is 2, then it will take 2 to the power 3 means 2 cube, that is 8 steps. If we use a single step during simulation, then the total number of steps is big O of n to the power 6. Okay, means a square of the previous one. If n is a polynomial in the input size, the running the notation of the polynomial time computability is quite robust, and Turing machine can preferably capture this notion. Okay, so thank you all. This is what about the modern computer and Turing machines.